Hi everyone, welcome to lecture number 10 of GG497 Geological Visualization. Today we're going to look at unconformities. We're going to see how we form an unconformity and the different types of unconformity that we can form. So unconformities then, they indicate the presence of time gaps within rock sequences due to erosion or non-deposition, and these might represent very long or very short intervals of time. If we have a look at the photograph on screen now, this is a picture of Hutton's Unconformity at Siccar Point. It's a world-renowned locality and was one of the first that allowed geologists to understand the deep nature of geological time, just how old the Earth and its processes are. What you can see in the bottom half of the picture is we have these steeply inclined sedimentary beds, and as we follow those bedding planes upwards, we see that they're all truncated along this contact. Above that contact we have a second series of sedimentary beds which are parallel to the contact and they're dipping at about 30 degrees or so to the left of the image. So the only way to really interpret this picture is that there must have been a period of time where these sediments in the bottom half of the picture were deposited. Then over millions of years these sediments, after being deposited, were tilted by some sort of tectonic movement. After they were tilted, over potentially millions more years, those rocks were eroded to form this uneven erosional surface that's truncated all of these older beds. And on top of that uneven erosional surface, more sediment has been deposited over potentially more millions of years. And then that whole system has been tilted again about 30 degrees to give us our current landscape. So all of those processes together are typically occurring over millions and millions of years of deep time, deep geological time. And that gap between the deposition and tilting of our lower beds and the deposition of tilting of our younger beds is a gap, a sizable gap in geological time where we're getting net erosion. Okay, so we can conceptualize these through another series of photographs. And the easiest type of unconformity to understand is an angular unconformity. So my question to you guys is, when we severely fold or fault rocks, what sort of topographic features are we likely to form? We're likely to form fold mountain belts. So for instance, things like the Himalayas or the Alps, if you were to look at the rocks in those places, you'd see that they were all folded up and they were all buckled. So we might form fold mountains. If we were to have an area that was severely faulted, we might form basin and range type topography, where we have mountains separated out by basins. But however we do form one of our mountain ranges through these different tectonic processes, we end up with a mountain belt which are susceptible to extreme amounts of physical and chemical weathering. So all of the rocks that go into building our mountain ranges are pretty quickly, geologically speaking, eroded. And it's these areas on Earth today that supply the majority of the sediment that's transported to the oceans. So we can see this process in a series of diagrams. We can have an initial phase of deposition where we start forming some sedimentary rocks. Then through tectonic processes, these originally horizontally bedded sedimentary rocks can be buckled, they can be deformed, they can turn into one of our fold mountain ranges, for example. And because of the extreme amounts of physical and chemical weathering in these fold mountains, they erode down quite quickly and we form this denuded surface where all of those rocks have been eroded to some level. And then continued deposition, maybe during a period of sea level rise or something like that. Continued deposition on top of this denuded surface means that we'll form new horizontally bedded rocks. And the horizontal bedding of those younger rocks and the tilted bedding of the older deformed rocks gives us what we call an angular unconformity. There's an angular difference between the dip of the beds beneath the unconformity and the dip of the beds on top of the unconformity. Okay, so angular unconformities are probably the easiest type to understand. But there are other types of unconformities. That the first type listed here is those angular unconformities where we have that difference in orientation of the beds either side of the unconformity. We can see that obvious erosional surface. A disconformity is where there's no real difference in the orientation of the beds, but there is an obvious erosional surface. So you can see the beds beneath the unconformity have obviously been eroded. There's an irregular erosional surface, but the layering in the beds below that erosional surface is similar or more or less the same as the younger beds deposited on top. A nonconformity is where there's a difference in the rock types either side of the unconformity. So for instance, where you have a metamorphic or igneous terrain, like maybe the depths of a mountain belt or some sort of volcanic arc system that has been eroded downwards to the igneous bedrock, and then on top of that igneous bedrock we've started to deposit sediments. So where we have a completely different set of rocks either side. And a paraconformity is where there is no difference in the orientation of the beds either side, but there's no evidence, or there's no significant evidence of any erosion happening. So between these two sequences of rocks there might be a large gap in geological time where there's not any deposition, but critically there isn't any erosion either, so it's just a gap where largely nothing has happened. So to see those in pictures then, this is what an angular unconformity might look like, where we have these differences in orientation of the beds either side of the unconformity. Here we can see a disconformity where we have these sandstones with these well-developed sedimentary structures. We can see this obvious erosional surface that's winnowed down into the underlying sandstones. But on top of that we've had younger sediments, and they still have more or less the same orientation in bedding as the rocks beneath the unconformity. This is a picture from the Grand Canyon where we have a non-conformity between our horizontally bedded sedimentary rocks, and they're sitting on top of a crystalline metamorphic basement. So two completely different rocks, obvious erosional surface between them, characterizes a non-conformity. While a paraconformity, there's no difference in the orientation of beds either side of the gap in geological time, either side of the unconformity, but that unconformity itself doesn't show any evidence of being erosional. It's a non-erosional surface. So there's just a gap in time where no sediment was deposited. So those top three examples, angular, disconformity and nonconformities, they're all evidenced by an erosional surface, and that's a period where the erosion rate in the area was greater than the rate of deposition. A paraconformity, you don't see that obvious erosional surface, and so we can interpret that during formation of a paraconformity, the rate of erosion is equal to the rate of deposition. That's why we don't see any net erosion, any obvious erosional surface. Okay, well, let's move on and ask ourselves how unconformable strata would appear on a geological map. Well, let's take a look at this fantastic exposure of a cliff. We can see that there's this horizontal or sub-horizontal unconformity upon which these sub-horizontal beds have been deposited, and they're more or less parallel to that unconformity. But beneath the unconformity, those older rocks, you can see that they've been severely folded. We've got these tight, not quite isoclinal folds that have been eroded to form an angular unconformity, on top of which these horizontally bedded what look like sandstones have been deposited. So to sketch out those elements, this is what we've got. We've got these folded rocks, we've got these fold axes, and these beds which have been folded have been truncated by this unconformity, upon which younger sediments have been deposited. Okay, well, let's imagine that we could take a bird's eye view of this section and imagine it in map view. If we look at the cliff at the highest elevations, going backwards into the cliff, we'd have our horizontally bedded sediments, those sediments which would have outcrop patterns parallel to the ground contours. But then in the lower elevations, as we went into the cliff and out towards the beach, the rocks that will be exposed are those folded sediments, where we'd see that repetition, that mirror imaging of the different rocks in the fold as we crossed the fold axes. Okay, so that's what our geological map would look like. We'd have these two packages of rocks, our older folded sediments, and the contact of our older folded sediments. When we got to the unconformity would truncate them, it would stop them. Those contacts, at least on map view, would not continue past our unconformity. Okay, so let's have a sort of a thought exercise based on a picture of a cliff. And this is an example of a real geological map which shows that sort of thing. This is from the Hawes sheet, which isn't too far away from Ingleton, where we would have gone before the world changed. But what you can see in Ingleton is you have these horizontally bedded carboniferous limestones, and you can tell they're horizontally bedded because of their outcrop patterns being more or less parallel to the ground contours. So you have this whole sequence of limestones, but then when we get here, you can see that we've got these strip-like exposures of Cambrian rocks, which, if you look closely, you can see symbols for fold axes, very tight isoclinal folding. We've got some antiforms there, we've got some anticlines there, and we've got some synclines there. And you can see that those older Cambrian rocks, as we follow the contacts along, they hit the unconformity and are stopped. So we have steep dipping beds, an angular unconformity between those steep dipping beds and horizontally bedded sediments. So here are our tightly folded Cambrian rocks, which are striking northwest and southeast. And these are our carboniferous rocks, which are horizontal. And that line between them, that contact point which truncates the outcrop patterns of the older rocks, that's our unconformity. So you can think of this little island as of Cambrian rocks. It's kind of like a little window beneath the younger covering to see those older features. You can see the same sort of thing in the Devonian and Carboniferous rocks and Triassic rocks near Bristol. Here we've got an antiform, which is caused by Devonian rocks, and then on top of that we've got layers of Carboniferous rocks. But then on top of that Devonian and Carboniferous strata we have an angular unconformity, on top of which these horizontally bedded Triassic rocks have been deposited, and you can follow the contacts in the Carboniferous rocks all the way up to that contact with the Triassic where they get cut off. Okay, so what's happening is the younger Triassic rocks are sitting on top of the Devonian and Carboniferous rocks, so when we make a map to show the rocks at surface, the contacts of the older rocks appear to be truncated by the Triassic rocks, and that's because they're sat on top of them. So we've seen angular unconformities before, and we can have a stab at drawing them in cross-section, and there is a little bit more that we have to do in terms of thinking when we draw one of these cross-sections that has unconformable rocks in them. So let's say that we wanted to go back to the horse sheet and draw one of our cross sections to show this unconformity and what's going on in the subsurface. Well, if we took a line between A and B, we can see that we go through the younger Carboniferous and the older Cambrian rocks, and further we can see immediately that we've got a lot of horizontally bedded rocks, so we're going to have to construct ourselves a hill profile. So just as we've done previously, we get our strip of paper and mark on our strip of paper the key topographic heights which will let us construct a hill profile. So I've just drawn the key ones. I don't want to draw them all because that would take forever. And then what I can do is take those hill heights and drop them onto my cross-section panel at the appropriate height and join up those marks to give me a hill profile between those 2 points A and B. So my hill profile along the horse sheet would look something like that. Then I can put my strip back onto the map and this time mark on my geological contacts. So I've marked on the two ends of my unconformity, and then I've marked on the contacts between the different rock types. Some of these things I've grouped together, like I'm not going to draw each one of these individual limestone beds. Instead I'm going to group them together. It'll just save me a bit of time without losing too much accuracy. And then I shade in the top of my strip the appropriate color, or I label it just so that I've got all of the information. Lastly, I annotate the strip with the dips or other structural information that I need. So all of these limestones, they're no dip, they're horizontal, all of those things are no dip. But I can see that my Cambrian rocks, they're very steeply dipping, they're tightly folded. So I've tried to draw an arrow showing the direction that I'm going to have to draw the contact on my cross-section line. Okay, how can I tell that this unconformity has no dip? How do I know it's horizontal? Well, same as with the contact in our Carboniferous limestones, the contact of the unconformity itself is parallel to the ground contours, and we can only get that if the feature is horizontal. Okay, now what I can do is take my cross-section strip and move my contacts from the cross-section strip to show where they'd hit the hill profile in the appropriate places. And I can transfer the rock types from my cross-section strip onto that hill profile just as a thin veneer on the surface, just to show what rock types are going to be there if I were to walk across this hill profile. What rock types would be on the surface. Okay, next I can draw the subsurface extent of some of the boundaries that I'm absolutely sure of. So for example, I know that those carboniferous limestones, they're horizontally bedded. And I know that those contacts I've got from my Cambrian rocks, they're steeply dipping, they're folded. So I can draw them. And then if I wanted to feel like I was making progress, I could add in the color for the areas of my cross section that I'm certain about. Okay, at this point we now have, maybe problem's not the right word, but we can't project the geology under the unconformity. We know that beneath this unconformable surface, we know that geology is still going on under there. This is very unlikely to be like a vast cave system that's just going to appear as a white box. There's geology, there are rocks down there which we're going to have to understand. We're going to have to try and interpret where they'd be. So what we need to do is go back to our map and extrapolate. So looking back at our cross-section strip against our map, underneath that area, that big part of our unconformity that we're not sure of, can we project any of the contacts in the Cambrian rock to where they'd be, where they'd intersect our cross-section if we were to continue them? Well, one thing that strikes me about this map is that I have this other core of a fold in the Cambrian rocks, and I can see it's got this strike that's going northwest to the southeast. So maybe what I could do is project that strike, continue it along strike to where it would hit my cross-section strip. Okay, so I can project these along strike with some degree of confidence. I mean, where else are these rocks going to go, right? They're just going to continue. If this unconformity wasn't here, then I bet these things would continue as strips and intersect our cross-section about there. We call this process of extrapolating rocks beneath this unconformity, we call this concept subcrop. So where would our rocks crop out at the surface if we didn't have this unconformity? In other words, where would our rocks crop out at a certain depth? Okay, so now that I've marked on my subcrop on my cross-section strip, I can move back to my cross-section and mark on where those boundaries, where they would subcrop or crop out beneath my unconformity. And here would be where those, if we projected those rocks along strike onto our cross-section line, that's about where they'd hit. So then what I can do is plot the dip of these rocks at the appropriate orientation, and I've measured on the cross-section of being about 65 and 75. Not quite symmetrical folds. And then what I can do is add color to the rest of my section. Now, underneath the conformity in this area, I can't project anything. I can't really project anything further, can I? I know from at least here onwards, if I were to project that along the same parallel strike, I'd be in that same material. However, what I'm going to try and do is show that I'm not 100% certain, because I can't see beneath the unconformity and I can't make a categorical interpretation beneath it. I'm going to add in my level of uncertainty to show that there's some undefined strata beneath this unconformity closer as I get to B. Then what I need to do is, to show I understand what is happening with the geology, I can project sensibly above the surface where the geology would continue. So for instance, these horizontally bedded rocks would be horizontal before this modern topography had formed. Those fold axes in my Cambrian rocks, they'd project up until the unconformity. And then what I can do is add a key, add the scale, add the labels, and any vertical exaggeration that I've used. Okay, so by doing that, we end up with a cross-section through these unconformable rocks. And if we were to compare our cross-section with the one supplied from the map, which you can kind of just about see the line goes along here, we can see that we're not a million miles away. We've got the topography, we've got a similar looking topography, but it's characterized by these carboniferous limestone rocks, which are angular. There's an angular unconformity between them and the underlying tightly folded Cambrian rocks. And you can even see on this cross section that the survey geologists have tried to show some of that uncertainty by fading in this bit of unknown here. Okay, so that's the end of our lab. Next week I think we'll look at a lab where we go through how we constructed geological history from a map, and then after that you'll have everything you need in order to tackle the assessment, which I'll put up on Student Central in due course. So now you can put this into practice and have a little go of the lead sheet where we have an angular unconformity, so you can have a look at the lab and see how you go about drawing your own cross section. Okay, thanks guys, see you later.